Hi friends, welcome back to my YouTube channel. So previously we have discussed error control and error detection. So what we are now going to do is we are going to discuss more about error detection part. So sorry, error correction part. So we have so many codes are there to correct or detect these errors from the data. So this is from module 2 computer communication EC 407 and it is based on the syllabus of KTU syllabus, Btech KTU syllabus. So if you are an electronics and communication engineering student, you can refer these notes for your exam. So ignore this part 2, this is not part 2, this is part 3. So I have mentioned it in a wrong format. So this is part 3. So we can go to the video. So first of all, we can discuss about linear block codes. So almost all block codes used today belongs to a subset called linear block codes. So the use of non-linear block codes or for error detection and correction is not as widespread because their structure makes theoretical analysis and implementation difficult. So we therefore concentrate on linear block code. So normally there are non-linear block codes are there, but these codes are very difficult to implement and very difficult for theoretical analysis. So we mostly concentrate on linear block codes. The formal definition of linear block codes requires the knowledge of abstract, particularly Galois field, which is beyond the scope of this reading. So therefore we give a informal definition. So you can see this table 1 and table 2 with data words and code words. I think you can refer the previous videos as well. You will get an idea what is data word and code word. So you must go through that videos and then come back here to watch this video. You will get a one idea about what is this data word and code word. So each data word have a particular code word is present. So let us discuss an example to understand the linear block codes. So let us see if two codes we defined in table 1 and table 2 belongs to the class of linear block codes. So these two tables are belongs to linear block codes. So the schema in table 1 is a linear block code because the result of XORing any code word with any other code word is a valid code word. So when we are XORing with any code word in the first with another code word, it's giving a valid code word. For example, the XORing of the second and third code word create the fourth one. So if you check this, if you go for code word 0, second one 0 1 1 and third one fourth one it is 1 0 1. So if you are XORing it 0 and 1 we will get 1 and 1 1 will get 0 and 1 0 we will get 1. So the resultant is XOR data is 1 0 1. So if you see the third one is 1 0 1. So that is the thing. So the schema in table 2 is also a linear block code. We can create all of our code words by XORing two other code words. So they can, in this one, the table 2, it describes like when we are XORing any two code words, they can create all other code words. So in a linear block code, the exclusive or XOR of any two valid code words create another valid code word. So that we meant by linear block code. So please put this in your mind that what is linear block code. So when we are XORing with any other valid two code word, it will create another valid code word. So that is all about linear block code definition. So minimum distance for linear block codes. So it is a symbol to find minimum Hamming distance for a linear block code. The minimum Hamming distance is the number of ones in the non-zero valid code word with the smallest number of ones. So minimum Hamming distance means the number of ones in the code word. And for example, if in our first code word table 1, so the number of ones in a non-zero code word are 2 and 2 and 2. So the minimum Hamming distance is dmin equal to 2. So in our second code, table 2, the number of ones in the non-zero code word are 3, 3 and 4. So in the code, the minimum Hamming distance is 3. So let's go to the table. So if it is mentioned that non-zero code word. So if you see, for first code word is everything is 0, so we can ignore that. In table 2 also, first code word is everything is 0. So consider all 3 other code words in both table. So both in first table we have 2 ones in every code word. In the second table, first one having 3, second one also having 3, and third one is also having 4. So we can see the dmin, the minimum Hamming distance of the linear block code is, for table 1 it is 2 and table 2 it is 3. So some linear block codes, let us now show some linear block codes. These codes are trivial because these can be easily finding the encoding and decoding algorithm for checking their performance. So a simple parity check code is a single bit error detecting code in which n equal to k plus 1 with dmin equal to 2. So one of the linear block code that we are discussing now, symbol parity check code. So which is a code, error detecting code, which is having n equal to k plus 1 with dmin equal to 2. That is the definition for symbol parity check code. Perhaps the most familiar error detecting code is the symbol parity check code. In this code, a k-bit data word is changed to an n-bit code word where n equal to k plus 1. The extra bit called parity bit. So it is selected to make the total number of ones in the code word even. So when we are getting a data word, we are making it as n code word by making k plus 1. We are adding one extra bit to make it even. So that bit is called parity bit. So it will make the entire code word with even. So although some implementations specify an odd number of ones, we discuss the even case. So the minimum Hamming distance for this category is dmin equal to 2. So which means the code is a single bit error detecting code and it cannot correct any error. So symbol parity check code is a error detecting code and it can only correct a single bit error by detecting, but it cannot correct any error. It can only detect the error, cannot correct any error. So if you see the figure, and in the first table, if you remember, the first table is a parity check code with k equal to 2 and n equal to 3. The code in table 3 is also a parity check code with the k equal to 4 and n equal to 4. So what it is saying, so in the table 1, if you see, the data weight is 2 bit and table 2 the data weight is 2 bit. So what they are doing, making it to a code word of 3 bit, it is adding 1 bit. So that means k equal to 2 and n equal to 3. And here in the table 2, k equal to 2 and n equal to 5. So that is there mentioned in the this sentence. So the figure you can show, there is a sender and receiver and data weight A3, A2, A1, A0, and there is a generator function, and then it is adding a parity check. So A3, A2, A1, A0 and R0. R0 is the parity check and is transmitted to the receiver, and receiver receives the code word as B3, B2, B1, B0, Q0. So these will go to a checker function and there it will generate a syndrome and it will accept or discard, that is there in the decision logic, and it will get the data word as A3, A2, A1 and A0. So figure shows the possible structure for an encoder at the sender and the decoder at the receiver. The encoder uses a generator that takes a copy of 4-bit data word. So it is taking a 4-bit data word, that means k equal to 4, and generate a parity bit of R0. So data word bits is a parity check bit to create 5-bit code word. So it is creating a 5-bit code word. You can see the table 3 in this figure. So this is the table 3 and it will discuss, data word is 4-bit and code word is 5-bit. The parity bit is 1. So that is the R0. So this is normally done by adding 4 bits to the data word modulo 2. The result is the parity bit. So in other words, R0 equal to A0 plus A1 plus A2 plus A3 modulo 2 function. So if the number is even, the result is 0. If the number is ones odd, the result is 1. In both cases, the total number of ones in the code word is even. So the parity bit is equal to, that means R0 equal to the code word, the data word. Data word means A3, A2 plus A1 plus A0. So we are adding here in XORing, that means modulo 2 addition is happening here. So if the number of ones is even, the result is 0. If the number of ones is odd, the result is 1. In both cases, the total number of ones in code word is even. So the sender sends the code word which may be corrected during transmission and receives a 5-bit data word. And checker at the receiver does not do the same. Does the same thing at this generator with the sender, with one exception. The addition is done over all 5 bits. The result, which is called syndrome, so is just 1 bit. The syndrome is 0 when the number of ones is received code word is even, otherwise it is 1. So syndrome is the sum of these 5 bits, addition of these 5 bits. So if the syndrome is 0, the number of ones in the received code word is even, otherwise it is 1. So S0 equal to, S0 means syndrome. S0 equal to B3 plus B2 plus B1 plus B0 plus Q0, and there also it is adding in modulo 2. So syndrome is passed to the designer logic analyzer. If the syndrome is 0, there is no error in the received code word. The portion of the data received and accepted as the data word. If the syndrome is 1, the data portion of the received code word is discarded and the data word is not created. So let us look at these transmission scenarios. Assume the sender sends a data word 1001, 1011. The code word created from the data word is 10111. That means 4 ones are there, that is even. So which is sent to the receiver. We examine 5 cases. First one, no error occurs. The received code word is 10111. The syndrome is 0 and the data word is 1011 is created. Second one single bit error changes A1. The received code word is 10011. So A1 is changed. So previously in A1 it was 0 and now the A1 is changed. So then we will get a syndrome of 1 and no data word is created. So there is an error. One single bit error in changes R0. So the received code word is 10110. You can check and manually you can check by this. So I am just giving an example. And the syndrome is 1, no data word is created. Note that although none of the data word bit is corrupted, no data word is created because the code is not sophisticated enough to show the position of the corrupted bit. An example of R0 and second error changes R3. The received code word is 00110. The syndrome is 0. The data word 0011 is created at the receiver. Note that here the data word is wrongly created due to the syndrome value. The simple parity check decoder cannot detect uneven number of error. The errors cancel each other out and gives the syndrome a value of 0. So that is happening. The errors are cancelled out each other. So we are giving a wrong syndrome value of 0. So the fifth one is 3 bits. A3, A2 and A1 are changed by errors. So the fifth one is 3 bits. A3, A2 and A1 are changed by errors. The received code word is 01011. The syndrome is 1. The data word not created, and this shows the simple parity check guaranteed to detect one single error. Can also find any odd number of errors. So simple parity check code can detect an odd number of errors. So for a better approach is the two-dimensional parity check. In this method, the data were organized in a table, rows and columns. So in figure, we can see the data sent 7-bit bytes. So are put in a separate rows. For each row, each column, one parity check is calculated. The whole table is then sent to the receiver, which finds the syndrome for each row and each column. So as a figure shows, the two-dimensional parity check can detect up to 3 errors. So that two-dimensional parity check can detect up to 3 errors that occur anywhere in the table. Arrows point to the location of the created non-zero syndrome. However, the errors affecting 4 bits may not be detected. In the first example, design of row and column parties. So there are column and row parties are there. So it is having 7-bit data is there. So one error affects two parties. So two errors affect two parties. So the arrows mentions the location of the created non-zero syndromes. And the fourth one is 3 errors affect 4 parties. And the fifth one is 4 errors cannot be detected. So this is not detected. So that is all about the symbol parity check. So next one is Hamming code. Hamming codes I think we have already discussed. We can just now go through that. So let us discuss the category of error detecting code called Hamming codes. These codes are originally designed with the d-min equal to 3. So the minimum Hamming distance is 3, which means that they can detect up to 3 errors and correct one single error. It can detect up to 2 errors and correct one single error. Although there are some Hamming codes that can correct more than one error, our discussion focuses on the single bit error correcting code. Let us first find a relationship between n and k in Hamming code. We see to choose that the integer m greater than or equal to 3. So the values of n and k are calculated from as n equal to 2 raised to m minus 1, where k equal to n minus m and the number of checks bits are equal to m. For example, if m equal to 3, then n equal to 7 and k equal to 4. And the Hamming code C7, 4 with d-min equal to 3. So table 4 shows the data word and code word for this code. So you can see this. As I said, the data word sender and receiver are there. Data word is A3, A2, A1, A0 and generators are there, and code word is A3, A2, A1, A0, R2, R1, R0. Like I said, the minimum Hamming distance is 3. So R2, R1, R0 is added as parity bit. So in the receiver side, they have a checker function and it will create a syndrome of S2, S1 and S0. So it will correction logic is there. So it will discard or accept. So above figure shows the structure of encoder and decoder for this example. So the data word is 4 and the code word is 7. That means for 3 bits of parity bits are added there. And R0 equal to A2 plus A1 plus A0, R1 equal to A3 plus A2 plus A1, R2 equal to A1 plus A0 plus A3. So these are modulo 2 functions. So a copy of 4-bit data bit is fed into the generator and create 3 parity checks R0, R1 and R2. So in other words, each of the parity check bits handle 3 out of 4 bits the data word. The total number of ones in the each 4-bit combination, 3 data word bit and 1 parity bit must be even. We are not saying that these 3 equations are unique. Any 3 equations that involve 3 of the 4 bits the data word can create independent equations are valid. So the checker in the decoder created 3 bits S2, S1, S0 in which each of the bit parity can check up to 4 out of 7 bits in the received code word. So S0 equal to B2 plus B1 plus B0 plus Q0, S1 equal to B3 plus B2 plus B1 plus Q1 and S3 equal to B1 plus B0 plus B3 equal to B3 plus Q2. These are summing in modulo 2. So equation used for checker, they are the same, and those used by the generator with the parity bits added to the right hand side of the equation. So 3-bit syndrome created 8 different patterns 001 to 111 that can represent 8 different conditions. So these conditions defined a lack of error or an error in one of the 7 bits of the received code word. So as shown in figure table 5, syndrome and error. So while we are getting odd 0, there is none, the error is none, and if we are getting 001, there is error in Q0, and 010, there is an error in Q1, and Q011, there is an error in B2, 100, there is an error in Q2, and 101, there is an error in B0, and 110, there is an error in B3, and 111, there is an error in B1. So this table distinguished as logical decision made by the correction logic analyzer of the decoder. So note that the generator is not concerned with the 4 cases shaded table 5, and because there is either no error or an error in the parity bit. So in the other 4 cases, one of the bit must be flipped. That means 0 to 1 or 1 to 0, and find the correct data word. The syndrome value in table 5 are based on the syndrome bit calculation. For example, Q0 is in the error, so is the first bit is affected. The syndrome therefore is 001. So B2 is in error, S0 and S1 are the bits affected, and syndrome is therefore 011. So that way we can consider. Similarly, if B1 is in error, all 3 syndromes bits are affected and the syndrome is 111. And there are 2 points we need to emphasize here. First, if 2 errors occur during transmission, the created data word might not be the right one. Second, if we want to use the above code for error detection, we need a different design. So we have 2 examples. Let us trace the path 3 data word from the sender to destination. The data word 0100 become the code word 0100011. The code word is 010001 is received. The syndrome is 000. No error. The final data word is 0100. And the data word 0111 becomes the code word 0111001. And the code word is 0011001 is received, and the syndrome is 011. According to table 5 is in error. By changing 1 to 0, the final data word will be 0111, and the data word 1101 becomes the code word 1101000. The code word 000100 is received. 2 errors are there. The syndrome is 101. So which means that B0 is in error. After flipping B0, we will get 0000, and it is a wrong data word. This shows that our code cannot detect 2 errors. So we need a data word of at least 7 bit. Calculate the value of k and n that satisfy the requirement. So we need to make k equal to n minus m greater than or equal to 7, or 2 raised to m minus 1 minus m greater than or equal to 7. So if we set m equal to 3, the resultant will be n equal to 2 raised to 3 minus 1 and k equal to 7 minus 3 or 4, which is not acceptable. So if we set for m equal to 4, then 2 raised to 4 minus 1 equal to 15, and k equal to 15 minus 4, which is 11, which satisfies the condition. So the code will be C, 15, 11. So the performance of these codes, the Hamming code can only detect a single error or detect a double error. However, there is a way to make it detect a burst of error. So the shown figure, the key is split the burst error between several code words, 1 error for each code word. And in data communication, we normally pack a packet or a frame of data. So to make the Hamming code to represent the base of error a size of n, we need to make n code words out of the frame. Then instead of sending one code word at a time, we arrange the code word in a table and send the bits to the table a column at a time. So in figure, the bits are sent column by column from left. In each column, the bits are sent from the bottom to top. In the way, a frame is made out of 4 code words are sent to receiver. Figure shows that the base error of size 4 corrupt a frame. Only one bit from each code word is corrupted. The corrupted bit in each code word can easily be corrected at the receiver. So this is the performance for if this figure shows like a best of errors can be split into several code words, and then it can be sent from left to right by column. So that is happening in the figure, so you can refer that. So that is all about today's, like we have discussed about linear block codes. First one is symbol parity check and another one is Hamming code. So please go through the notes and this video. If you like this video, please subscribe my channel, like, share and comment. If you have any doubt or if you need any clarification, please let me know and put the same in the chat as well. So thank you so much for watching my video. See you in the next video.